Hello everyone, I'm Ruiyao Jiang. Today, I will introduce the supercapacitor. For the first part, I will introduce the history and evolution. We can see the timetable. Orange in 1957 proposed supercapacitors, and in 1966 developed the first commercial practical device. And then in 1978, NEC used the name supercapacitor for the first time. Since the 1990s, advances in materials technology have driven their applications. Examples are electric vehicles and electronic devices. After the 2000s, new materials such as graphite promotes its application. Examples are transportation, energy, and 5G. In recent years, hybrid supercapacitors are emerging. For the second part, I will introduce types and working principles. We can see the three parts. First, electrochemical double-layer capacitor. Electrostatic effect. A double electric layer is formed at the electron-electrolyte interface. Low energy density and high lifespans. The example like rose carbon, activity carbon, carbon arrow, and graphite. Next is cedar capacitor. Redox, reversible Friedel reaction, high energy density and low lifespans. The example like transition metal oxides and conductive polymers. The last is hybrid supercapacitor. The principle of lithium batteries, the combination of EDLC and cedar capacitance, good comprehensive performers. Example like lithium-ion electrons. The third part, I will introduce the electrode used. For the first part, I will introduce the electrode materials, determines the capacitance type, energy density, and conductivity mechanical properties of supercapacitors, and its called link of performance optimization. According to the material type and performance characteristics, common electrode materials can be classified into the following four categories. First, carbon-based materials, low cost, large specific surface area, good electrical conductivity. The main material of EDLC, improved power density and circle life. Electrical double-layer capacitor. Example like activity carbon and graphite, but the cedar capacitor performance is limited. Second is metal oxide, high cedar capacitance and high energy density. Cedar capacitors example like manganese dioxide, but some materials are expensive and have relatively low stability. Next is conductive polymer, strong electrical conductivity and good flexibility. See trouble on variable supercapacitor, example like PANI and PPY, but the long-term stability is relatively poor. The last is composite material, fusion of high conductivity and high cedar capacitance, and optimization of electrochemical properties. Example like graphite plus PANI and CNT plus manganese dioxide. But the synthesis complexity have increased. The next part, I will talk about the basic concepts of electrical conductivity and resistivity. We can see the last part. Electrical conductivity depends on the number of electrons and mobility. Next is material classification. Metals, conductors, semiconductors, and insulators. Next is conductivity foundation. Supercapacitors, electrical materials, example like graphite and activity carbon. We can see the right part is very important formula. Is sigma equals 1 over rho. conductivity is sigma, whereas resistivity is rho. Next, I will introduce the dielectrical materials and capacitance principles. We can see the left part. There are three different formulas. First is the basic charge storage principle of capacitors. C equals Q over V. And then is Paulus place capacitance formula must in vacuum. C equals epsilon naught A over L. Next is after inserting the dielectric. C equals epsilon A over L equal to epsilon rho plus epsilon naught H over L. And then we can see the right part. Relative dielectric constants is epsilon. Two energy storage machines, double layer capacitance and see the capacitance. The important part is the principle of the electrical polarization and charge separation. And then I will introduce the conductivities and electrical conductivity. First is electrical conductivity. It depends on the free flow of electrons in materials. And then is in ionic conduction. It relies on ion migration. And then it affects electrical conductivity, like temperature and defects and dropping. First, temperature. An increase in temperature raises the number of free carriers in semiconductors and enhances electrical conductivity. And for the defects and dropping, impurities and grain boundaries and these locations can scatter electrons, affecting electrical conductivity. Impurity contains its gravity and electron defect rate. And then I will talk about the role and characteristics of electrolytes and polymers electrolytes in supercapacitors. First is electrolytes. The key medium for the migration of ions between electrolytes, energy storage, and release. First, common forms. Liquid, slit-scale electrolytes, lampolite and ACl solution. Next is electrolytes classification. Strong electrolytes, weak electrolytes, and non-electrolytes. Next is ionic hydration process. Ionics interact with surface molecules. The last is ionic liquid. Low volatilities, wide liquid temperature range, and high thermal stability. And then is polymer electrolyte. For this is solid state, gas state, supercapacitor. First is common types. Polymer salt complex, polymer electrolytes, and then is performance requirements. Ionic conductivity is over 10, and then is development forms, gel electrodes, solvent plus polymer, and other composite materials. The last is application field, solid-state supercapacitor material. And then I will talk about the machines of ion migration in supercapacitors and the application and advanced of fast ion conductor materials in solid electrolyte. First is ion conductor machine. Supercapacitors rely on the repeated migration of ions between electrons, meaning achieve thought ion hopping and the movements of polymer change segments. Amorphous polymers have relatively high electrical conductivity. And then for the fast ionic conductor, solid electrolytes are used in high-performance supercapacitors. Beta aluminum, sodium ion conductor, and gamma silver iodide high temperature, and high conductivity. The performance depends on the ion migration activation energy and the vacuum machines in the crystal structure. And then I will talk about the factors affecting the performance of supercapacitor. First, ionic liquid, high performance electrolytes, low volatility, and elastic thermal stability. And then polymer electrolytes, flexibility and high stability, flexible supercapacitor. Second is electrode materials, improvement of ion migration efficiency and optimization of electrolyte designs. Example like beta aluminate, and then electrolyte characteristics. The core requirements for performance improvement are high ionic conductivity and wide potential window. The last, high ion conductivity materials, high specific capacitor materials, sample like silicon, enhance the energy storage capacity of the capacitors. And packing technology, soft pack structure achieve lightweight, sample like flexible and variable capacitors. Next, I will introduce the different electrode types and conductivity machine determine the energy storage performance and environmental adaptability of supercapacitors. First is liquid ionic electrolyte. Store the charging medium and determine the power density. Next is polymer electrolyte. It is used in steady-state supercapacitors to enhance the stability of the electrolyte. Third is ion conduction machine. Determine the charging and discharging speed and energy conversion efficiency. The last is ionic liquid, high voltage window, low volatility, green and environmentally friendly. For the fourth part, I will introduce the advantages and disadvantages. We can see the left part. I will introduce the advantage of the supercapacitor. First, high power density. Over 10 kW over kg, rapidly resisting a large amount of energy. Next is fast charging and discharging speed. It takes several seconds to several minutes to complete the charging. Next is long circle life. Charging and discharging up to millions of times. And then one operating temperature range. Extreme environmental range from negative 50 degree centigrade to past 70 degree centigrade. And then it's high security, stable with no risk of thermal runaway. And then it's simple maintenance. No complex management systems is required. And the last is green and environmentally friendly. The materials is non-toxic, recyclables, and cause little pollution. And for the right part, we can see the disadvantage of the supercapacitors. First is low energy density. It's from 5 to 10 Wh over kg for lower than that of lithium batteries. The second is high cost. Some materials, pre-cross materials and graphite are very expensive. And then is the self-discharging rate is high. Electrical energy is difficult to maintain for long time. The last is low voltage limit. High voltage requires multiple single cells to be connected in series. And for the fifth part, I will introduce the recent development. We can see the 8 parts for this. One is high specific energy designs. Graphite and metal oxide composites with specific energy exceeding 50 Wh/kg. Next is flexible wearable applications. The device can be bent and stretched for smart wearable device. And then is miniaturization. Miracle supercapacitors, micro robots, and sensors. And then is environmental friendly manufacturing across electrolytes and biomass carbon, cocoa shells carbon, seaweed carbon, and then solid electrolytes, device safety and energy density improvement, optoelectronic products, and then is graphite material. High electrical conductivity and large specific surface area have enhanced energy density and charging the discharging speed. And then is nanoelectrode structure. Structures such as nanowires and nanotubes have improved the surface area and capacitance performance. And the last is hybrid structure. The integration of materials and capacitors enhance energy density and circle life. In the last part, I will introduce new trends and technology. First, we can see AI assist designs. Artificial intelligence optimizing electrolyte materials. And then is flexibility and self-healing technology. Supercapacitors are stretchable and self-healing light wearable device. And then battery and supercapacitors mobile system. High energy density and high power integrated output. And then is photoelectric hybrid device, integrating solar energy and supercapacitors. And then green manufacturing, production through low carbon and environmentally friendly methods such as combining waste and using natural materials. And then is high energy density materials, exploring two-dimensional materials. And then is solid electrolyte, enhance surface and voltage ranges. And the last second, sustainable materials, testing renewable resource to promote the development of environmentally friendly energy storage. And the last is integrated design, electronic components integration, mini-adduce high-performance device. Okay, my presentation is over here. Thank you.